Continuing our talk about differentiability, here's our seventh graph. It consists of a linear on the left of 0 and a quadratic on the right of 0. Draw the derivative graph for this function. The slope on the left appears to be 1/2. I'll draw a horizontal line at y equals 1/2. The slope on the right starts at 0, where there's a horizontal tangent, and then gets steeper and steeper in a negative direction. Remember, that's a quadratic, so the derivative should be a linear. Both of the values of the derivative function for the red piece on the left and the red piece on the right, there are holes. Okay, so we cannot find the slope at 0, and we're going to talk about why. All right, so we've drawn the derivative. Let's talk about continuity. At x equals 0, is f of x continuous? F is not continuous. Let's make that look correct. Not continuous. Because why? F of 0 is 3. The limit as x approaches 0 from the left and the right does not exist, and therefore the two cannot be equal, the function value and the limit value, so the function is discontinuous. Okay. Again, do we have an abrupt change in slope from the left to the right? Slope on the left is 1/2. Slope on the right starts at 0 and gets more negative. We have an abrupt change in slope. So f of x is not differentiable at x equals 0. Why is that the case in this scenario? This is different than the other scenarios we've looked at so far. F of x is not differentiable at x equals 0 because f of x is not continuous. This is the only graph we've looked at so far where we don't have a continuous function at a particular location. Okay, so let's take a look at some summaries here. What is the prerequisite for a graph to be differentiable? If you said continuous, you are correct. On the graph of f of x, describe 3 characteristics you may see which result in non-differentiability. Remember, differentiability is the ability to take a derivative. If you cannot take a derivative, what's happening on your graph? 1, you could have a sharp point, also called a sharp corner, or also called a cusp. Number 2, you could have a vertical tangent. And number 3, you could have discontinuity. Remember, what does discontinuity look like? It could look like a hole. It could look like a vertical asymptote. Or it could look like a jump. All right, let's write the definition of derivative for a function. Remember, we looked at f prime of a. I want you to do f prime of x. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. When does a limit exist? Well, a limit exists if the left-hand limit equals the right-hand limit. Because the derivative is based on a limit, we need to know that the left-hand slope equals the right-hand slope for the limit to exist. Another way to say that, a little more mathematically, is that f prime at some value of x on the left, so the slope of the function at c on the left side of c must equal the slope of the function at c on the right side of c. Okay, last two ideas, very important ideas. If a function is differentiable at a point, then the function is always what? Everywhere this graph was continuous, we had a derivative. When the graph was not continuous, we did not have a derivative. So if a function is differentiable, it implies that that function is continuous. Continuity is a prerequisite for differentiability. If a function is continuous at a point, then that function is only sometimes differentiable. When is a function continuous but not differentiable? At a sharp corner or a vertical tangent. Okay, these are the only notes that we did in class today. What we did next was we started to look at homework. On the back of the worksheet, I guess if you're getting it from the website, it's 2 different pages, but there's a worksheet on continuity and differentiability. This is spelled incorrectly, but okay. All right, so question 1, the graph of the function below. Note on your graph, if you're printing this out, these are open circles. Every other point is a closed circle. For what numbers on the interval from -3 to 3 is f not continuous? Explain your answer. F is not continuous. Well, let me look for holes, asymptotes, or jumps. So at x equals -2, at x equals -1, and at x equals 2. Explain your answers communicating mathematically. So I would say, for the first one, the limit as x approaches -2 on the function f of x is defined as -1. The function value at -2 is defined at 2, but the two are not equal. For x equals -1, the limit as x approaches -1 on the function does not exist. Therefore, the function is not continuous. We could say f of -1 is 1, but the two are not equal, so the function is not continuous at -1. Third one, when x is 2. So as x approaches 2, the limit from the left does not equal the limit from the right. And in fact, f of 2 does not exist. We don't say these two are not equal, but they are not equal. And we don't have continuity. If either the limit or the function does not exist, you do not have continuity at that point. So that would be these would be good explanations for why your function is discontinuous at those points. All right, let's talk about differentiability. When is this function not differentiable? Well, automatically, what do you know? Wherever f is discontinuous, which is at -2 and -1 and +2, the function is automatically not differentiable. Okay, but what else do we have to consider for non-differentiability? We need to consider vertical tangents and sharp points. Do we have any vertical tangents? No. Do we have any sharp points? Yes. F is discontinuous at x equals 0 because f prime of 0 from the left does not equal f prime of 0 from the right. And at x equals 1 because f prime of 1 from the left does not equal f prime of 1 from the right. All right, let's keep going with the homework here. Okay, for this question, we're given a piecewise function. I'm going to rewrite that piecewise function as x squared minus a squared over x minus a when x does not equal a, and 0 when x does equal a. All right, let's re-express this first piece. The numerator can be factored. Remember, whenever you see a rational function, it is in your best interest to factor to find out what's going on. So we have x minus a times x plus a over x minus a. Well, what happens when we reduce this function? You've got it. This really is the same thing as saying I have x plus a when x does not equal a, and I have 0 when x does equal a. Okay, I want you to think of a function. Pick a value for a, any value you want. I want you to visualize what this function looks like. I'm actually going to move that down. So I'm going to pick an a value of 3, just to kind of get it in my head. All right? So if a is 3, I'm looking at x plus 3 when x does not equal 3, and I'm looking at 0 when x does equal 3. Okay, so 1, 2, 3, there's a 0. The line x plus 3 is a positive linear sloped line passing through -3 and +3. And when x does equal 3, we have to have a hole All right, so there's my line with a hole in it. What is the y value of the hole when x equals 3 on my function? Well, if you take the limit as x approaches 3 of my function, x plus 3, you're going to get 6, and that is what it is. Okay, now you could just go back and say, all right, well, it's really not 3, it's really a. It's really a. It's really a. It's really a. But now I want to know, what would my y value be as x approached a for this limit? Well, a plus a is not 6, it's 2a. All right, now let's answer some questions. Is f of x defined at a? Is my function value defined at a? F of a equals, well, sure it is. It's told to us in the function definition itself. So f of a is 0. All right, does the limit of f of x as x approaches a exist? Limit as x approaches a on the function f of x, does it exist? Well, when you walk along your curve from the left and you walk along from the right, what do you get closer and closer to from either the left or the right side? You get closer to 2a. So yes, I might even say this, the limit as x approaches a of x plus a equals 2a. Oh, it's kind of like what we wrote over here, huh? All right, good. Is f continuous at a? Well, no. There's a hole, dear Liza. Where's the hole? There's the hole at a, 2a. And we're going to say, look, the function value was 0. The limit value was 2a. And these two things are not equal.